In physics, work is done on an object, for example our box here, when a force causes a displacement of that object. So in our example here, our object is a box, and this person here is providing a pushing force against this box. Now if this box travels a distance of d meters, then the work done on this box is equal to the constant force applied to this box multiplied by the distance this box moves. Now the important thing to notice here is that the direction of this force is the same as the direction of the displacement, and there are no other forces acting on this box. So this box is being pushed on ice, so there are no frictional forces. And let's imagine our person here has crampons on. As this person pushes this box with a constant force over this distance, this person is adding energy to this box. And if you think about it, if you're pushing something on ice on a frictionless surface, even if it's only a short distance, the box will gain a velocity. And when you stop pushing against this box, the box will continue moving in the forward direction forever. And this box will have a certain energy in its system. So work, the units of work are newtons times meter or joules. If we're pushing this box with a force of 10 newtons, and we do this over a distance of 10 meters, the work done on the box is equal to 100 joules. And this 100 joules is the energy that's been provided to this system, this box here. What happens now if we provide a constant force to this box that has an angle theta to the direction of motion? Well, the work done on this box is equal to the force on the box multiplied by the distance the box moves multiplied by cosine theta. And the reason why we're multiplying this by cosine theta is because we're only interested in the horizontal component of the force, because the horizontal component of the force is parallel to the direction of motion. If we draw a triangle, the adjacent side here is the horizontal component of the force that we're interested in, and that's F cosine theta. So for example, if we're pulling at this box at an angle of 30 degrees to the direction of the displacement of the box, and we've got a force of 10 newtons, and again we're moving this box 10 meters at an angle of 30 degrees, the work done on this box is equal to 100 multiplied by 0.866, which equals 86.6 joules. This means that we're imparting less energy to this box simply because the angle doesn't align with the displacement vector. What happens now if we push our box with a force F along a surface that's not completely smooth? We have to take into account the force of kinetic friction. So now we've got two forces acting on our box at the same time. So how do we work out what work is done on this object if we're able to move the box a distance of d when friction's involved? In this situation, our force is parallel to our displacement. In other words, the angle between the two is 0. Cosine 0 is equal to 1. So the work done by this pulling or pushing force is equal to the force multiplied by the distance. If this force again is 10 newtons and we're moving a distance of 10 meters, the work done is equal to a positive 100 joules. So we're giving 100 joules to this system. But the friction is trying to take energy away from this system. In other words, if we remove this force, so we no longer have this force pulling or pushing at the box, and this box is in motion, the friction will eventually slow this box down. And as it's slowing this box down, it is removing energy from this box. So what's that mean in terms of work? So in terms of work, the work is equal to the force, whatever force is being applied to the box, in this case the force of kinetic friction, multiplied by the distance the box moves. So in this case, the box is sliding to a stop over a distance of d. Let's imagine that distance is 2 meters. We do need to add this cosine term now, because the force of kinetic friction does not point in the same direction as the displacement that the box is moving in. So the box is moving in this direction for 2 meters until it comes to a stop. The force of kinetic friction is slowing down the box over time. Let's say this force of kinetic friction is equal to 10 newtons again. The box is moving a distance of 2 meters. But what's our angle between our force and our displacement? What's this angle here? Well, this angle is 180 degrees. Because the force is pointing in this direction, but the displacement is pointing in this direction. And this angle here is 180 degrees. So what is cosine 180 degrees? We get -1. So our work is equal to -20 joules. Now this is only an example here, but what I wanted to illustrate was this negative term here. The sign of work can be positive, which means we're adding energy to the system, the box in this example, but the work can also have a negative value, which means we're taking away energy from the system. So let's go back to our original example where we have two forces acting on our system. So we're pulling our box along, but the force of kinetic friction is also acting to slow down our box at the same time. So in this situation, we have to find the net force acting on this box. So we got the force pulling the box forward, minus the force of kinetic friction. And that equals our net force. So our net work on this system is going to equal the net force multiplied by the distance the box moves, multiplied by the angle between the resultant force and the displacement vector.